Eh, Bienvenidas al tercer día de esta conferencia. Esta sesión es parte del bloque B con el tema de cosmología y física de partículas por la profesora Marta Losada. En este momento también está la charla en el bloque A, que es de física de partículas, a cargo de la profesora Miriam Mondragón Ceballos. Pero les recuerdo que pueden ver luego la grabación de la otra sesión en nuestro canal de YouTube o en la página web. Sí, muy bien. Como mencioné, en esta clase es de cosmología y física de partículas eh, y va a ser dada por la profesora Marta Losada. Ella es una física teórica de Colombia y actualmente es profesora de física y decana de ciencias de la Universidad de Nueva York en Abu Dhabi. Obtuvo su doctorado en física en la Universidad de Rutgers en Estados Unidos y desde el 97 al 99 fue postdoc en el CERN, en la división de física teórica. Ha sido investigadora principal de numerosos proyectos de investigación centrándose en la fenomenología y cosmología de partículas elementales y en la física experimental de altas energías, y miembro de múltiples proyectos de colaboraciones internacionales, incluidos los experimentos Atlas, DUNE y NEXT. Es miembro del Comité Científico del Simposio Latinoamericano de Física de Altas Energías y del CERN, de la Escuela Latinoamericana de Física de Altas Energías. Y recientemente fue nombrada presidenta del grupo preparatorio de la Estrategia Latinoamericana de GECAP. Estamos felices de tenerla en esta sección de cosmología y partículas, y recuerden que si tienen preguntas, no duden en levantar la mano, y ahora las dejo con Marta. Adelante, profe.
Okay. Gracias, Daniel, por la invitación. I'm going to speak in English. Okay. So, thanks to Danielle and to all the organizers for this initiative and for inviting me to give a talk today to all of you. So the title of my talk is Persistent Cosmological Puzzles and their Relationship with Particle Physics. And so this is what I'm going to be focusing on. All right. So the two building blocks of our understanding for particle physics and cosmology are the standard model of particle physics and the standard cosmological model. And one can say that essentially all that directly makes up our life on Earth is really determined by the standard model of particle physics. But that is not the case when we look at the cosmos. So I'm going to introduce some main cosmological puzzles and try to clarify how they relate to particle physics and look at some connections between the phenomenology and experimental results that we have. I think it's extremely important that even though we may be interested from the theoretical or phenomenological point of view, we're very aware of the experimental results. So I'm going to be very keen on highlighting this throughout the lecture. So the goal is to elucidate deep connections between fundamental particle physics and cosmology, but I'm going to focus on a couple of very specific examples. And just to keep in mind, there are going to be many, many fundamental questions that I will not be talking about today. So if we look at the fundamental forces in nature, this is our real starting point. And so here on the table, you can see which are the four fundamental forces in nature. So of course, we have the gravitational, electromagnetic, weak and strong forces. And if we look at their long distance behavior, we see that even though the gravitational and electromagnetic forces scale like 1 over r squared, the weak force has a very different dependence on r, and as well as a strong force. And likewise, if we look at the relative intensity, we can see that the strength of the interactions are extremely different. So if we're taking the alpha strong, the strength of the strong force to be 1, relative to that, we can see the weak force is just 10 to the minus 6 less intense than the strong force. And similarly, the electromagnetic force is 10 to the minus 2, and the gravitational is, in some ways, one would say, oh, it's completely irrelevant. It's 10 to the minus 39. It's a huge, huge difference. But let's focus on just the electromagnetic and the weak interactions. There are two fundamental differences in these forces. One of them is that one is long range. The electromagnetic, as I said, scales as 1 over r squared, while the weak force has this exponential suppression and as a function of R. And the other thing is who actually feels these interactions, right? But let's just pose this question. What would happen if the electromagnetic and weak interaction weren't distinguishable? Well, the short answer is that the universe would be completely different. I have to hold on because my light turned off. I'll be right back. Sorry about that. So then now we've talked about the fundamental forces. And so which are the elementary particles that are feeling, especially the forces around the weak, the electromagnetic, and the strong interactions. Those three forces can be described within the context of a symmetry group, the SU3 cross SU2 cross U1 symmetry group. And here we have all of the particles that are present in the standard model. So in the outer ring here, we have all of the fermions in the standard model. And the ones that are above this mid diameter are the quarks, and below we have the leptons. Then in the next circle, we have what are the bosons that carry the electroweak, strong, and electromagnetic interaction. And right in the center, we have the Higgs boson. If you look on the right, you can see all of the, sorry about that. You can see all of the different interactions that occur among these fundamental particles. So, you know, a quark will interact with both a gauge boson, like a W or a Z, but it can also interact with the Higgs boson. And very importantly, it interacts with the gluons, while the leptons will never interact with the gluons. So this is just kind of showing us the different interactions that are possible. And very interesting is to see that this Higgs boson can also interact with itself. And in the simplest model, which is the one that is posed by the standard model of particle physics, the intensity of the interaction is proportional to its mass. Now, here's also a nice graph that is telling us, you know, how long did it take from the actual concept of this particle to its actual discovery. And so we have, again, the differences in the electron, of course, which was the first particle that was posed back in the 1880s. And it took, you know, maybe a couple of decades or so, a little less, to be discovered. On the other hand, we have the latest particle, which is the Higgs boson, all the way down here. And you see it's theorized back in 1964 and then discovered only in 2012. So we're in a great moment now, almost, you know, slightly over 10 years after the discovery of the Higgs boson. But let me go back to a very important aspect about the electromagnetic and weak interaction. So at low energies, we know that they are different. But what happens when we go to higher energies? They actually can be unified, and this was shown by Glashow, Weinberg, and Salam, into one unique electroweak force. But if that is true, then it's absolutely essential that there have to exist neutral currents. And this wasn't something that was known before. At the same time, when the Higgs mechanism was proposed, it was quickly realized that you could have this mechanism that would break this electroweak symmetry, and as a consequence, it's going to give them the gauge bosons and the fermions some mass. Very importantly, the photon remains massless as a consequence of electroweak symmetry breaking. So which are the first steps from the experimental point of view? Well, actually, we're now roughly 50 years after the discovery of neutral currents that happened in Gargamel at CERN. Subsequently, also at CERN, there were two other experiments, UA1 and UA2, which were responsible for discovering the W and the Z boson. And then we had subsequent colliders like LEP and Tevatron, and they made many, many more precision, what are called precision electroweak measurements, measuring the mass of the Z and the W, gauge couplings, and actually what was the Z width. So let's try to understand this even better, even more. So what is the way that this electroweak symmetry breaking occurs? So at very early times in the universe was hot. The Higgs field had zero vacuum expectation value. So it is like sitting at the top of this kind of Mexican hat kind of potential, right? But as the temperature lowers, there seems to be some kind of breaking of the symmetry. This Higgs field then will roll down to this other vacuum state. And when that happens, what is actually occurring to the other elementary particles is that they feel the background Higgs field. And here's a nice cartoon made by Jorge Cham, in which he's really showing, kind of trying to give you an intuition of what's happening when this Higgs field acquires this vacuum expectation value that really permeates all of space-time. And the fact that the different particles are feeling this Higgs field in a different way and is correlated to its mass allows it to see what would be the difference of the effect within this background of the Higgs vacuum expectation value. So let's go back to the standard model. So we said that the basis was to have a Lagrangian. The symmetries of that Lagrangian are the SU3, SU2 cross U1. And the Lagrangian actually seems to be quite simple to write. And this mug here has actually the Lagrangian written in it. So the first line here is just telling us all about the gauge bosons and their interactions. The second line is really telling us about how do gauge bosons interact with fermions. The third line is telling us about how do the fermions interact with the Higgs field phi, and the last line is all about the Higgs field. It has a kinetic term, and then it's going to have a potential term as well. So the crucial elements are the symmetries of the Lagrangian described above, what is the mechanism of electroweak symmetry breaking, and what is the particle content representations. So the standard model, Lagrangian, is going to define our particle interactions. And we can see here, let me try to get rid of this, sorry. The particle decay, so if you have a particle A that's decaying into these two other particles B and C, that's going to have a decay width and decay rate. You can have annihilation, so you can have, let's say, an electron and a positron. They can annihilate and produce a third particle, or you can just have scattering. So the particles will interact by, in this case, a gauge boson, and they will just scatter off. But the important thing to note, of course, is that the strength of the interactions are defined by the gauge couplings and the Yukawa couplings, which are noted here just by G sub I and Y sub F. And the Higgs potential parameters are the self-coupling lambda and the vacuum expectation value, V. So everything is very well defined in terms of very concrete set of couplings. And with that, we can calculate all of the necessary physics from decays, annihilations, or scatterings. Let me make one note in terms of effective theories. So even though this may be the fundamental interaction that is happening here in this case, a scattering via the W gauge boson of the electrons and muons, if we are in a regime in which the mass of the W boson is much, much larger than Q squared, which is the square of the momentum exchanged in this scattering, then one can actually understand this as an effective four fermion interaction that is on the graph on the right. And that will just have an effective coupling, which we call G Fermi, and that coupling will just be some number that you can calculate by multiplied by the gauge coupling, the weak gauge coupling squared. Oh, actually, this is a typo, to the fourth, sorry, and divided by MW squared. And in fact, this same type of graph, when you have a muon, which has a decay, decays to an electron, a neutrino, and a muon, it decays to an electron neutrino, and a muon neutrino, we can measure the muon decay and from there extract GF. And because of this relationship with the mass of the W gauge boson, this will actually define the vacuum expectation value. And it turns out to be 246 GeV. So if we go back to the previous slide, we have all of these parameters that are all going to be well defined by measuring either the decay or these scatterings, etc., all except the self-coupling of the Higgs boson are defined by that. Now, let me switch to what is the standard cosmological model, in which we just use the acronym lambda CDM. So in standard cosmology, we're looking at a universe that is evolving, starting from a homogeneous and isotropic background universe with very small inhomogeneities that are characterized by having a certain statistical distribution. And in that case, then the universe can be described by the Friedmann equation, which is this one in the box. Whoops. And here we just have the sum of what is the energy density of all of these particle species that are summed up here, plus a term that comes from what is the energy density of the cosmological constant. Now, it turns out that all of our observations of the universe are such that we see is a flat universe. And in that case, K will be exactly equal to 0. So that means that the sum of these energy densities, omega I plus omega lambda, is going to be exactly equal to 1. And so in this case, the cosmological model is parameterized by only 6 free parameters, and these can also be determined by different observations. But very, very importantly, and we'll see it in more detail further on, it's going to require that there exists dark matter. And it also is important to note that no fundamental standard model particle can be the dark matter of the universe. So we definitely are going to need new physics. So the high energy physics frontiers. So basically there are 3 frontiers that we want to consider. We have on the first case, the energy frontier, and then we have, which is the blue circle in this graph, then we have the cosmic frontier, and finally we have the intensity frontier. So I'm going to focus throughout this talk basically on the energy frontier. We've already talked about the origin of mass, what happens when the Higgs mechanism breaks electroweak symmetry, gives masses to the fermions and the gauge bosons. That's what we're talking about, the origin of mass. Actually, according to the Higgs mechanism, was also giving mass to itself via the self-interaction. And then we have some of these other issues that are arising here in the intersection between, say, the intensity frontier and the energy frontier related to the matter-antimatter asymmetry in the universe, or what I just referenced, dark matter. And again, I also mentioned very briefly at the end of the last slide that with this, all of the discussion before is leading us to really need to consider what would be the new physics beyond the standard model. So these are kind of the main topics that I'm going to discuss as we go forward. So let's look at the energy frontier. We have the Large Hadron Collider. It results in the discovery of the Higgs, and we can actually measure the physical properties. But it's really important to highlight the following. The Higgs is the only known elementary spin-zero particle. That means that it's a scalar. And we've been able to measure the standard model properties of this Higgs boson that was discovered at the LHC. So it does have the short range weak interaction. And we can look at it from looking at the decays from the Higgs to a pair of W's or Z's. And Hayashikawa interactions. They exist. The other result from this energy frontier is that there are no new elementary particles discovered with masses all the way up to, say, a TeV. So this means that if there is no physics, it probably is high enough to be able to be parameterized via higher dimensional operators. These would be operators that we would add to the Lagrangian that are more than dimension 4 operators. And if we do have new physics via higher dimensional operators, wouldn't it be interesting for us to try to use Higgs physics results from the LHC to try to constrain these higher dimensional operators? But also, we might consider that these dimension 6 terms, for example, if we look at the particular term that involves a coupling of the Higgs to a fermion field, it could actually have complex couplings. And what would be the consequences of this result? So you might have seen this before, but I think it's just good to be include this just to be consistent and cover all the topics. So we have the Large Hadron Collider. So it's this collider that is located at CERN, and it is really this huge ring that's 27 kilometers has a circumference of 27 kilometers, and you have protons colliding on protons, and you have 4 big large experiments with the detectors. And in this case, you have Atlas, Alice, CMS, and LHCb. Very briefly, just to see the detail of one of these detectors, you have the Atlas experiment, and so it's going to be made up by different subdetectors. So you're going to have, in first case, the inner detector, and this is made up by different types of silicon pixels, silicon strips, transition radiation detectors. But what the important thing is that this is the part of the detector that is giving us precise tracking and vertexing of the outcoming particles from the collision of the protons on protons. Then we're going to have the electromagnetic calorimeter and the hadronic calorimeter, in which you're going to essentially see the deposits, the energy deposits of, in the first case, what would be electrons and photons, and in the second case, what would be mostly the hadrons that are coming out. And finally, you have the muon spectrometer as well. And so the muons, which are, just like the electrons, but like 100 times heavier, will typically fly out and hit these muon detectors. Now, the LHC has had several runs, and up to run 2, it had been able to deliver for 13 TeV, like 147 inverse femtobarn. And here we just can see the delivered luminosity for each one of the runs at the different center of mass energies of the collider. The reason I bring this up is because a key parameter is the integrated luminosity. Once you have the integrated luminosity, if you know the cross-section of the event that you're looking at, then the number of events that you expect to have is related by this equation right here. And it's very important to realize what the implications of running at a higher center of mass energy. For example, if you're looking at the production of Higgs boson when it's through the interaction with top quarks, you're going to have a 4 times higher value of the cross-section at 13 TeV with respect to what you have at 8 TeV. So here are the different Higgs production modes at colliders. So you can have you see the 4 different Feynman graphs on the right side of the slide. So you have the first graph here. This is gluon-gluon fusion, and it will produce Higgs. You can have also what is called vector boson fusion. So you have 2 quarks, and here you have these gauge bosons, and they also will fuse and produce a Higgs boson. But here, in this case, you will have 2 forward jets, this Q1 prime and Q2 prime. You can now also have the VH production, in which you have the production of the Higgs boson associated with the gauge boson when you've already had the quarks annihilate and produce gauge boson. And finally, you will have what is called the QQH And in particular, the largest contribution to this is the TTH. So when these Qs are actually the top quark, and you will also be able to produce a pair of top quarks in conjunction with the Higgs. So the LHC has been able to measure all of these cross sections. So the table here on the left is actually showing us what is the value of the gluon-gluon fusion cross section, for example, with respect to the expected standard model value. And you see that there's quite a good consistency with what is the standard model value. And of course, this will improve with time as you have more statistics and you make more measurements. So a quantity to keep in mind is this normalized cross-section value to the standard model value. And in particular, if you also want to look at specific decay modes, what you want to see is the normalized cross-section times the branching ratio, that is the decay rate over the total width of the Higgs, in this case, to what are the standard model values. So keep this in mind, this definition of the normalized cross-section times branching ratio. So what was the huge success of the first run of the LHC? This was done with 7 and 8 TeV, and it was actually the discovery of the Higgs and establishing what was the value of the mass. So as a result of all of these analyses, essentially looking at only 2 channels for the Higgs, we have the Higgs decaying to 2 photons, or Higgs decaying to 2 Z gauge bosons, which then decay to the 4 leptons. You can establish that the mass of the Higgs should be around 125 GeV. The most interesting thing is that once you know the mass, then now every single parameter is completely defined in the standard model, okay? Everything is fixed. So if you come down here, you see that then this lambda, which was the self-coupling of the Higgs, is given just by this ratio of the mass of the Higgs to the vacuum expectation value squared. And so this is equal to about 0.13. At the same time, you know, before we knew what was the mass of the Higgs boson, we would have, you know, plots of what would be the cross-section of producing in, you know, a collision of protons, Higgs plus X as a function of the mass of the Higgs, or we could look at the decay width, or we could look at the branching ratios of the Higgs. But once you have the mass of the Higgs well defined at 125, then you know exactly what are these values of the branching ratio. So I'm just giving you an example right here in the bottom right corner of at M Higgs of 125. This is going to be the branching ratio, say for Higgs to BB, it's around 56% and so on. And so this is really a fantastic experimental result. Then we have in run 2 is really probing Yukawa couplings. So you may remember the term in the Lagrangian that coupled the fermions to the Higgs. So that term does 2 things. When the Higgs gets a vacuum expectation value, it will give the mass to the fermions. But in addition, you will have what will be the interaction of the Higgs. And if the standard model is correct, then there's a very clear relationship between the value of the mass and the value of the Yukawa interaction. And here you have the plots for both Atlas and CMS, in which you see the strength of the interaction as a function of the particle mass. And because you see this very, very strong correlation to what is expected from a standard model Higgs boson. You see all of the data points sit really right on this dashed blue line. Now below, it's very important to see the degree of uncertainty that we have when we're actually measuring the strength of this interaction. And it's, again, normalized to the standard model value. So if it were exactly a standard model, you would expect all the measurements to be at 1, but of course, not all measurements are infinitely precise, so you're going to have some error bars, and this is the uncertainty that we have for each one of the Yukawa couplings that we are measuring in this case, okay? So very importantly, up to now, we have no new evidence of new particles apart from those that were already in the standard model coupling to the Higgs. And then another aspect that is really important is we've now determined what is the Higgs mass value. We knew what was the top quark mass value. And having both of them has huge implications for the vacuum stability of the universe. It has implications on what is the nature of the electroweak symmetry breaking. And we can actually understand what are the implications in terms of what would be the electroweak phase transition. But we crucially want to measure the Higgs self-coupling to understand what is the shape of the scalar potential. So even though we know that this should be the value of this self-coupling, we actually need to measure it. So let me just say a little bit more in terms of high luminosity LHC projections. We're going to want to, at a larger center of mass value and with more integrated luminosity, we're going to be able to increase our precision in determining the values of these Yukawa couplings. So here's a projection of how one would increase from the current values to the future values of the Yukawa couplings for each one of these fermions. And also included here are the gauge bosons W and Z. And if we want to look and understand what will be the projection for the high Lumi LHC in terms of the self-coupling, you can see here that at least you'd be able to exclude the value of a zero value of the self-coupling at 95% confidence level for the full luminosity of the high Lumi LHC. And then a future collider like the FCC would expect to have a sensitivity on the order of 5% on this self-interaction strength. So there's, of course, much more Higgs phenomenology. I don't have time today to cover all of that. But one thing to consider is that the Higgs could be the portal to any new physics. So you could imagine that the Higgs boson could be the only field that couples to other beyond the standard model particles, and some of them could be scalar particles or fermions or other gauge fields. And in fact, one could also argue that each one of these could possibly be a dark matter candidate. So let me now go to the cosmic frontier. So when we look at the universe, there's been really accurate measurements of what is the energy density distribution of the universe. So this graph on the left is showing us now, we know pretty well that our ordinary matter is only making up slightly less than 5% of the energy density, while dark matter is around 26% and dark energy around 68%. But these are all fundamental of unknowns that we have. What is dark energy? Nobody really knows. What is dark matter? We don't know what it is in essence. And when we look at the universe, we see all of this 5% is really ordinary matter. But we all know that antimatter exists, but it's not present in the universe in the same amount as ordinary matter. So where is all the antimatter? And I'm going to try to talk about this puzzle, cosmological puzzle. So we have a very precise measurement now of the asymmetry of the matter-antimatter in the universe. And if you look at the abundance of baryons in a co-moving volume, you would now know from the measurements done by different experiments, including Planck, that this value is going to be like on the order of 10 to the minus 10. And if you start off with a universe that has no asymmetry, then how do you actually make a matter-filled universe? So back in 1967, Sakharov established what was absolutely needed in any model or any theory that would be able to generate the asymmetry between matter and antimatter. On one hand, you would have to have baryon number violation, you would have to have departure of thermal equilibrium, and you would have to have C and CP violation. And I'll come back to these again further along. But let us look at in a little bit more detail of the universe composition. We know the universe is electrically neutral. We know that electrons and protons have essentially equal number densities. We know that positrons and antiproton number densities are essentially zero. We also know that in the early universe, it was radiation dominated, and that photons and neutrino number density scales as the temperature to the cube. But these are the persisting cosmological puzzles. When we look at this schematic evolution of the universe, we have what is the origin of the matter-antimatter asymmetry? And it could have occurred at different moments in the evolution of the universe. It could be at very, very high temperatures. And so the models of grand unified theories would be the ones that could, in principle, generate that matter-antimatter asymmetry. It could occur at the same time as the electroweak phase transition. That's what's called electroweak baryogenesis, electroweak bow. And then you'd expect it to be related to Higgs phenomena. Finally, you could think of another moment in the universe at intermediate values of the temperature or time, and this would be models of leptogenesis, and these would be related to neutrino phenomena. Hold on 1 second again, please. Another persistent cosmological puzzle, as I was mentioning before, is dark matter. And one can consider solutions of dark matter both in the context of standard cosmology or non-standard cosmology. And finally, one can consider neutrinos and dark matter. Is there any relationship between these two types of particles? So let's just kind of really go and try to understand the baryon asymmetry of the universe. So we have a matter-antimatter asymmetry. If we had equal quantities right now in the universe, what we would be seeing, particle and antiparticle annihilating. And these would, produce gamma rays, and we see no significant amounts of antimatter near to us. There are no gamma ray emissions within the cosmological horizon. And it's actually very difficult to have domains of matter and antimatter at this scale. We're talking about 100 gigalight years. And there are only really a small fraction of antiprotons in electromagnetic showers that are coming in through cosmic rays. But again, if we go back to the Lagrangian, to the fundamental physics laws, we see that particles and antiparticles have essentially the same laws. So how do you get this tiny, really tiny difference of, 1 in 10 to 10 in between the matter and that antimatter? So if we look at the cosmic microwave background or the Big Bang nucleosynthesis, you could imagine that matter-antimatter asymmetry could be an initial condition, but that doesn't give us a response of how it was created. On the other hand, anything that had been created before inflation would be eliminated by inflation. It would eliminate any primordial asymmetry. And of course, at the end of inflation, when the inflaton is decaying, you could consider that as it decays, and that time is called reheating, there are two options. You could either have a reheating process that is matter-antimatter symmetric, so then you would have equal amounts of matter and antimatter, and so then baryogenesis, or this asymmetry, can only develop dynamically after reheating, or alternatively, it could be produced during reheating. But imagine what would be the consequences of not having this production of the baryon asymmetry. So within the standard model, even at temperatures of order of the GeV, you have the equal abundance of protons and antiprotons. It is only at temperatures around 20 MeV that the freeze out occurs. You have the annihilation of protons and antiprotons going into a pair of pions. That cross-section is roughly given by 1 over the mass of the protons squared, and then the number density for protons is equal to the number density of antiprotons, and it's given by this expression here. This is the equilibrium density. At freeze out, then the number density times this cross-section is going to be essentially equal to the Hubble constant at this temperature. And that means that you will stop tracking the equilibrium density as it's described by this equation here, and you'll end up with a relic abundance on the order of 10 to the minus 18. This is way, way too small. As we said, this should be on the order of 10 to the minus 10. So which are the actual measurements that we've been able to make to determine the existence of the baryon and the consistency that the baryon asymmetry of the universe exists? So we have the abundance of light elements, and this graph on the right is showing precisely the light elements of like lithium and helium and deuterium and their relative abundances to hydrogen as a function of what is called this parameter eta, which is just a baryon to proton number density ratio. And you see that it has a certain dependence on this. But so to have to successfully produce the light elements during this period of Big Bang nucleosynthesis requires that the baryon asymmetry of the universe is in equilibrium, thermal equilibrium, for temperatures that are greater than, say, 4.7 MeV. That means for times smaller than 0.03 seconds. Of course, the bow could have been produced between reheating all the way up to BBN, but typically is considered to occur at the temperature on an order of 100 GeV. That means that time is only 10 picoseconds. The other thing that one can measure using the cosmic microwave background is baryon acoustic oscillations. So if you have the baryon to photon ratio will modify what is the actual sound horizon. And this is going to shift the peaks of the power spectrum that you measure in the CMB to larger values of the multiple moment L. That means smaller angular scales. So this is kind of the way you calculate the sound horizon as a function, again, of the variation in eta. And these would be the peaks, as you see, are here depending on this sound horizon value. So once you do that, you can actually see this yellow band here, which is determining what would be this baryon to photon ratio and how it is consistent with the production of the light elements in the graph that's there on the right, top right. So Planck parameters measuring CMB can actually give you what is the energy density of baryons. You get a very precise measurement, and if you combine it with the baryon acoustic oscillations that I just mentioned, you get a very, very precise measurement. And then you can relate that to the actual abundance of baryons given by NB over S. This is exactly the same as this value YB. So you can plug this value that you get in for omega BH into here, and then find what is the value of NB over S. And then you get this exact value of 8.59 times 10 to the minus 11. So remember, Sakharov had outlined what were the characteristics of a dynamical mechanism that could produce the asymmetry in the abundance of matter over antimatter. So you'd have to have baryon number violation. In the standard model, you only have B plus L violation. You don't have independently just baryon violation. I'll describe a little bit more this B plus L violation in a couple of slides when I talk about sphalrons. But essentially, the condition is that you need the baryon and the Hamiltonian not to, baryon number and Hamiltonian not to commute. Now, you also need C and CP violation, according to Sakharov. And CP violation was actually discovered in the standard model back in 1964. However, it's much too small, and it won't allow you to produce the necessary amount of the asymmetry. And finally, you're going to need a departure from thermal equilibrium, because you need the thermal densities of the particles and antiparticles to stop being in equal thermal equilibrium. However, there has been no evidence for perturbative baryon number violation or lepton number violation at zero temperature. That means that unless we can use this B plus L from sphalerons, we would need new physics to be able to have that. As I said before, the CP violation measured in the kaon system is much too small. So we need a new mechanism that will bias particles from antiparticles. And the mechanisms that we know pretty well of how to produce non-thermal distributions of particle abundance are basically related to two effects. One, when you have particles decaying in the background of an expanding universe, or if you have a phase transition. The challenge here is, if we add new physics, how do we prove that this new physics is really producing the baryon asymmetry of the universe? And there are many possible models, and I will only talk about two of them in the rest of this first lecture. And I'll focus only on electroweak baryogenesis and leptogenesis. Again, let me just be clear. We don't know what is the new physics scale. It could range from milli-electron volts to, tens of or thousands of tera-electron volts. But what we do know is that the energy ranges that have been covered by experiments seem to imply a couple of things. The new physics scale could be high enough for the standard model to just be an effective theory. And secondly, it could be that we only have very weakly coupled new physics to the standard model. So now I need to explain about sphalerons. In any Yang-Mills theory, that is a local gauge symmetry, you will have this topological effects of sphalerons. And this is kind of a description of what you can see in the Yang-Mills vacuum structure in this plot on the right. So you have like an oscillating graph that is showing, different vacua. And at T equals 0, very small values of the temperature, it is only through quantum tunneling that you would be able to violate B plus L. But this is extremely suppressed. However, if you go to higher temperatures, then your sphaleron processes that violate B plus L can be unsuppressed. And they could be the sphaleron condition to convert, say, lepton number into a mixture of baryon and lepton number. But it has very important implications. If, for example, net baryon or lepton number had been created in the early universe, this would, as was kind of hypothesized, say, in grand unified theories, this net B baryon number, lepton number would be washed out by the sphaleron processes, because they would be all the time having this kind of unsuppressed conversion of the baryon and lepton numbers. They would be really in equilibrium. And secondly, it's very important that even though the sphaleron processes violate B plus L, they conserve B minus L. So if you had created a net B minus L, this will remain intact in spite of sphaleron processes. So you could imagine some models in which you could actually do that. But here we go back to the relevance of the phase transition and the relevance of the dynamics of the electroweak phase transition. What you need to suppress these sphaleron transitions below, say, 100 GeV is for the Higgs to acquire a large vacuum expectation value, but also that the transition be a first order phase transition. And there, in that way, there will be an effective suppression of the sphalerons. The standard model cannot accommodate such a solution. For that to happen, the mass of the Higgs should have been around 70 GeV or smaller. Now we've measured it, it's 125 GeV. However, we do have some beyond the standard model options in which you will have all the ingredients for a new CP violation or a strong enough electroweak phase transition. So you need to do a detailed study of the electroweak phase transition in the context of these beyond the standard model. And it's challenging to understand which are the relevant degrees of freedom and the dynamics that will govern the properties and characteristics of the electroweak phase transition. So just to give you a sense of how this works, you have a hot plasma with all of your particle content of the standard model, or if you're looking at a beyond the standard model, you have them as well in this hot plasma. But you have a net zero baryon number with electroweak symmetry. The universe is expanding, it's cooling, then the electroweak phase transition occurs at around 100 GeV. You have bubbles of the broken phase nucleate and expand to fill the universe. And you need to have new physics for two things. You need to have CP violation sources. That means that the plasma particles have a CP violating interaction with the bubble wall, and you need to have this strong first order phase transition to suppress those Faleron transitions in the broken phase. So you can assume you have no degrees of freedom that produce a strong first order electroweak phase transition. They may not affect the CP violating interaction with the bubble wall, and you don't need any new sources of CP violation from the new degrees of freedom. There are important parameters to take into account, which are the wall velocity, the wall width, that need to be obtained in every specific model, and I'll just show you a few examples. Here again is pictorially we can envision how these processes happen. So suppose you have these charged fermion plasma, they have CP violating interactions with the bubble wall. We have outside of the bubble wall, the Higgs Bev is zero. Inside, we have a non-zero value of the Higgs vacuum expectation value. And when you have these interactions with the bubble wall, you're generating a chiral asymmetry. You all are going to have strong Faleron processes. You're going to have electroweak Faleron processes. Again, in the symmetric phase, the asymmetry that has been produced, this chiral asymmetry that has been produced, is diffusing in the symmetric phase, and this is somehow washing out the net amount of your asymmetry. But at the same time, you have the bubble wall that is growing and catching up, and at some point, the bubble wall catches up and freezes in the net result of the baryon number density into the broken phase. All of this can be calculated in a lot of detail, and I'm not going to go into this. I'm just going to show how you do this in a very simply. If you have the particle densities, they're going to satisfy this kind of transport equation in which you have several different terms. You have the Yukawa type interactions for these fermions. You are going to have the strong Faleron terms. You're going to have the weak Faleron terms. You're going to have a relaxation term as well. But importantly, you're going to have a CP violating source term. And then you can use the diffusion approximation to correlate this to the wall velocity and the diffusion constant. And you will generate a net value of the baryon asymmetry. Simple example, if you take the standard model and you extend it with just dimension 6 terms that involve the Higgs field with the fermion fields of this type, you can define these two parameters, TR and TI. I'm not going to go into the details, but I'm just going to show you two results in which in the parameter space of these TI and TR, you could have below this red line. This means that you're generating a large enough baryon asymmetry. The blue lines are the constraints you're getting from collider physics, from the Higgs decay, from the measurement of the Higgs to tau tau. What is the allowed range of these two parameters? And you also have another constraint coming from electric dipole moments. And this green region is telling you where you can actually satisfy all of the constraints. So this is just one model. And on the left, it's when you have not only, say, a tau source, but a bottom and a tau source, you could actually enlarge the region of parameter space in which you can have a viable electroweak baryogenesis. Okay, so I'm going to stop here for now, and we will continue with the other topics in 10 minutes. All right? When I was talking about the baryon asymmetry of the universe, I mentioned two possible mechanisms that I wanted to talk about, and this is the second one, the leptogenesis. So neutrinos, we do know that they have a mass as determined by experiments. The mass is going to be on the order of electron volts. And the seesaw mechanism is one way to explain the small value of neutrino masses. In the case of the seesaw, what one does is to add single neutral fermions to the standard model. And you're going to generate the lepton asymmetry via the decay of these single neutral fermions called heavy neutrinos, also in a CP violating way in an expanding universe. And then the lepton asymmetry is going to be converted to a baryon asymmetry via Sphaleron processes. So here are some minimal neutrino mass models. On the top left, you have what would be a Dirac mass, in which you just are adding this right-handed neutrino to the standard model. It doesn't exist. And for this reason, neutrinos don't get mass in the same way as all the other fermions. And this could come from a term in the Lagrangian that looks like what is here with the red noir term and a coupling lambda. So when the Higgs gets a BEV, you would just get a mass that is proportional to that lambda coupling and the Higgs BEV. And this is also illustrating what would be the corresponding Feynman interaction, Feynman diagram for the interaction. And on the right, we have what would be a Majorana mass term. So in this case, the neutrino is also its antineutrino. It's the same particle. And this kind of a mass term could come from this higher dimensional operator, L phi by L, indicated by this diagram here. And it needs to be corrected by this 1 over lambda energy scale. So the mass term would actually go like the coupling times V squared. You have the two Higgs fields and suppressed by 1 over lambda. So that is exactly what you can imagine. As I remember when I showed the effective theory, this is kind of a point interaction, but this could actually be illustrated by the seesaw mechanism. So you have this additional term in the Lagrangian, and because this noir can also be a Majorana mass, you can also add this type of second term, which is a Majorana mass. This would be indicated by this diagram here. If the mass of the right-handed guy is very heavy, then this would simply give you this other coupling, and that limits or generate the neutrino mass. So, as I said before, for leptogenesis, you would have the out-of-equilibrium decay in a CP violating way of this heavy right-handed neutrino, and is going to decay into a lepton and a Higgs, or it can also decay into the lepton bar, Higgs bar. So this is the case when you're going to look out of equilibrium is when the decay rate is going to be smaller than the Hubble rate. So you're going to have to look at the in a decay rate, and on one hand, it's just going to go like lambda squared times the mass, which is going to be related to the neutrino mass, because lambda is related to the neutrino mass. And if you want to look at what is the CP violation that is produced in this type of decay, you need to look at the difference of the decay is going to the particles, or the decay of the same particle going to its antiparticles. And these are the kind of diagrams that would contribute. You cannot stay only at tree level. You need to see the next correction to have the proper interference. And in any case, then the CP asymmetry is going to be proportional to the imaginary part of the product of this these lambda matrices. So you're going to have, in the standard leptogenesis scenario, when you're considering masses of n to be greater than 10 GeV, you're going to have an out of equilibrium decay. And basically on the right, you're going to see what is the evolution of this particle number density. So it starts out of equilibrium, can rise to equilibrium. At the same time, you're here producing the net B minus L. You could have also resonant leptogenesis. This would happen at the order of 100 GeV, but this requires a high mass degeneracy in more than one heavy neutrino. You can also consider the impact of flavored leptogenesis. That means that when you calculate the final value of the lepton abundance, it's not just a simple product of the CPA asymmetry times the efficiency of the process, but there is a flavor structure, flavor dependence in the final result. And you can also have an enhancement at very low scales. Typically, you wouldn't expect you to be able to generate the right amount of the asymmetry, because when you're going to very low values of the masses, you need to have very, very small couplings. But you actually can in this mechanism, which is slightly different when you're looking at the production through neutrino oscillations. And there is a very important flavor effects as well that are in place. So you can here on the right see what would be the generation of the baryon asymmetry, in this case of low scale leptogenesis. The interesting thing is then to relate it to colliders. If this, here we see that all the different experiments that are going to be sensitive to the mass of this heavy right-handed neutrino, and as a function of the mixing that this field can have with the left-handed neutrino. So you can see the region in which you could have the right amount of the baryon asymmetry from the bound on the baryon asymmetry, and all the different sensitivities that the different experiments that have been proposed. Some are fixed target experiments, some are the collider experiments in the future. On the right, you can see what would be the limit from the LHC. But you can also consider the case in which you're not looking at prompt decays in the LHC, and this is what's shown in this plot. You know, the full sensitivity when you also consider that you might have a displaced decay of this heavy neutrino. And so you now see that when you consider the displaced decays, you're actually coming into the region with the LHC, the region in which baryon asymmetry is viable. So just to sum up, with the very high scale leptogenesis, you can clearly produce the baryon asymmetry of the universe, but you cannot actually falsify that model. It's not accessible experimentally. Low scale leptogenesis, you would be able to, in principle, measure some kind of effect in these type of experiments that are here in this graph. Okay, so let me move to dark matter. So dark matter, we have our essential motivation arising from astrophysics, originally looking at rotation curves for galaxies, and now the X-rays from clusters. And let me highlight both Zwicky and Vera Rubin for the excellent work that they did in really identifying and in the case of Zwicky, postulating the existing of dark matter, but Vera Rubin, the systematic discrepancy that she measured between the predicted and the observed angular motion in galaxies. But again, as I mentioned before, we just don't know what is the dark matter energy scale. And it can range along the scale that's in this graph here, and then you'd have different types of possible dark matter. You have a very popular mechanism, which is called the WIMP, the general WIMP mechanism. And one of the reasons for it to be really exciting, a model, is that you have a model who has a large coupling, has a mass that is accessible for us in a large number of experiments, and you'd imagine you can, and the best result of that combination of the coupling and the mass is that you get the right dark matter abundance that you need. So let me just kind of let's look at this graph here on the right. If chi is the particle that is representing dark matter, and you want to see there are 3 different types of interactions with quarks. You could have just the scattering of the dark matter with quarks, and that's what's used in direct detection. You could have, if you look at the graph from above, you have the annihilation of dark matter, and it could be producing, quarks or leptons as well. And then you could have the production of dark matter in colliders. So you have, like in the case of the LHC, proton-protons colliding and producing dark matter. You have all of those possible options. So when you calculate the annihilation cross-section, and you again look at what is the cross-section with respect of these annihilations, at some point in the expanding universe, then you're going to have a freeze out of this non-relativistic dark matter particle. So that basically says that the abundance is going to be following this blue curve in this case. So you are in equilibrium all the way out until you reach freeze out, and then you freeze in to the measured value of the dark matter abundance. So this is telling you really that the energy density related to the dark matter is going to be inversely proportional to this thermal average cross-section, annihilation cross-section. And this is very important because we can measure these or put limits on the values of this cross-section when we do direct dark matter searches, or when we're looking at collider dark matter searches. On the other hand, there are many, many options for different models for dark matter. So here we have those that are related to the weak scale, and the technique that's used experimentally to try to find these particles are nuclear recoils. On the other hand, you could have ultralight dark matter particles, and then you would have to have very different experiments to try to measure the existence of these particles. And these are the 2 types of dark matter models that I will talk about today. There's no way that we can cover all of them. But again, if we go to the WIMP miracle, what happens is that you have the cross-section, the annihilation cross-section times the velocity is going to be on the order of g weak to the 4th over the mass of dark matter squared. And that is what allows you to, in the nuclear recoil experiments, to have, possibilities of detection. But that's not the only possibility. This graph here is actually showing us, if you have, as a function of the dark matter mass and the coupling, you could really sit on several other regions in parameter space, which would be WIMP-less dark matter, so non-WIMP miracle. As I said, the ultralight dark matter, or you could even consider modified cosmologies. So let's go focus on the direct detection. So for the larger masses of possible dark matter candidates, you'll look at essentially differential recoil spectrum and nuclear recoils. But even to do that, that modeling is going to rely on several different inputs from different fields. You're going to have to know really well what is your cross-section from particle physics. You're going to have to understand nuclear physics effects, and you're also going to have to understand your astrophysics really well. Here, I'm just going to flash some of the results, the current results in the nuclear recoil type experiments, the exclusion plots as a function of the WIMP mass and the cross-section. And you can see these very competitive experiments, Wantan and Lux and Panda, all really, really hitting for masses above 10 GeV, on the order of 10 to the minus 46 centimeters squared in the cross section. That's extremely impressive. And you start to hit really into the region of the neutrino floor. So you're going to have neutrinos that are, you know, background to possible signals from nuclear recoil in this type of experiments. And on the right, you're seeing what are the future limits that are expected from all these other experiments that are either proposed or under construction. And so essentially you see you're hitting really the neutrino floor. So the question is the WIMP miracle still possible? And so there's a nice analysis that looks at the exclusion plots within the context of two specific models, which I'm not going to detail what they are, but they're the green region and this kind of brown region here. And you see that you essentially have excluded many of the regions, but not all of the possible regions still of these models. And on the other hand, it's also useful to see on the right-hand plot if what would be really the possible complications once you're so close to the neutrino background to distinguish some kind of signal. So for example, the Higgsino, if it were the, you know, the dark matter, would be completely immersed into the neutrino background, while the Wino would not. Now, as I said before, you can also search for dark matter collider. And remember the Higgs portal that I talked about before. You could think of having the Higgs decaying to, say, a pair of scalars. So you produce the Higgs from quarks, and then you have a decay into scalars, and these are actually dark matter. And so this is an analysis that has been done, for example, in that atlas, looking at all the different types of particles, either scalar particles or fermions or gauge particles, and the limits that have been put. And it's impressive, the limits that have been placed on the values of the cross-section of the WIMP with the nucleons in this case. Another alternative to dark matter is the ultralight dark matter. So anything that is going between 10 to the minus 12 to around 10 to the minus 22 eV to around keV could be dark matter. The difference, of course, as I mentioned, is the different type of experiments that you can do to actually measure this type of alternative solution. So let me just tell you a little bit about the main features of ultralight dark matter. It's such a small mass, and that would mean that it has to have a very large occupation number per de Broglie volume. So it has to be bosonic, it cannot be a fermion. So imagine as you consider that you have a scalar field that is going to oscillate with a certain Compton frequency. So this phi field is given by some amplitude phi 0 and some oscillation sign of the, which is defined by the mass. The Compton frequency is defined by the mass of the particle. So the local dark matter density that has been measured is going to tell you, you know, what will be the value of this phi naught. And so you can see that it's on the order of 10 to the 10 GeV when your mass is scaling like 10 to the minus 22. So the oscillation period, which is just going to be given by 1 over the mass, is on the order of about 1.3 years times this factor here. So this is the range of masses that we can consider. Now, neutrinos have a long history. I won't go into all of the details about neutrinos, but I'm going to try to relate the ultralight dark matter to neutrinos. And so the important thing is that, you know, from experiments done, you know, in the late 1990s and early 2000s, there's a final solution confirming that neutrinos undergo oscillations. So the probability of when you start off with the production of, say, an electron neutrino, after some time, the probability that it continues to be electron neutrino is not 1. And these neutrino oscillations can be parameterized through a rotation matrix. So this is the matrix that is going to relate the mass eigenstates from the flavor eigenstates. And so this is the most general form of this rotation matrix. But then we know in the standard model, we have three left-handed neutrinos, the electron neutrino, the muon neutrino, and the tau neutrino. But we don't know why their mass is so small. We don't know what is their absolute mass scale. We do know that from the experimental point of view, in the neutrino oscillation experiments, there are two important mass differences, either delta m squared atmospheric or delta m squared solar. But we don't know what is the hierarchy of the neutrino masses. And this graph here is just showing you the relative value compared to the other fermions in the standard model. And we do get a constraint from cosmology that the sum of the left-handed neutrino masses must be smaller than like about 0.2 electron volts. So neutrino oscillations, in the two neutrino case, you imagine just say neutrino, the oscillation between two flavors of neutrino, then the probability is going to go like the sine squared of twice the mixing angle times the sine squared of the mass squared difference times the length of the distance that is being traversed or divided by the energy. Yes, Danielle? You have a question?
Yes, I have one.
Please go ahead.
The CP violation in this sector could be enough to fulfill Sakharov's conditions?
So when I was talking about the leptogenesis, yes.
So we need like heavy neutrinos?
Yeah, so that was the case that I showed before in the leptogenesis model. You'll have new couplings, and because of the interference effect, you would have a CP violating decay, and that can be large enough to satisfy Sakharov's condition.
But in this case, for example, that we have the new sources of CP violation in the PMNS matrix.
Yeah, so you cannot produce it just with the PMNS value.
Okay. Thank you. Yeah.
All right. Okay, so neutrino experiments are difficult. Neutrinos have only weak interaction and are very, very hard to detect. So I just want to give you a sense of how hard it is. You can produce, say, a proton beam and have it hit a target, and you're producing, say, 10 to the 12 protons per second. Of that, only about a tenth of the initial intensity will be pions that are produced at the target with a certain energy above 2 GeV and within a certain geometry. These pions then will have a certain decay length, and about 10% of the pions will decay. So the flux is going to be like 10 to the minus 9 of the initial intensity. So you're going to have just about only one event per hour. However, this simple experiment that was proposed around 1960 was the first neutrino beam that led to the discovery of the difference between the electron neutrino and the muon neutrino. So now let me go to this setup. Within the case of the ultralight dark matter, we have extra terms in the Lagrangian from the standard model. So we have a dimension 5 term. This is the same term I showed before that generates neutrino masses in the seesaw mechanism. And then we have another term in the Lagrangian, which is coupling this ultralight dark matter field to the Higgs and to the lepton fields. And here you have lambda is going to be the scale of new physics. Now, both Z here and Y are 3 by 3 symmetric matrices. So this is going to generate first the neutrino mass term, as we saw before. It just got generated as well. But now you're going to have also a Yukawa coupling term of the neutrinos with this ultralight dark matter field. And so what happens is that you're going to modify the mass square difference in this way, very specifically. This is the usual mass square difference, but you're going to have an extra term that is going to depend on Y. And you can parameterize this in terms of this eta value, eta delta. And similarly for the mixing angle, you will have a modified value of the mixing angle, and it's going to be there's going to have a new term here that modifies to theta hat, which you can parameterize as with eta theta. Give me 1 second, please. So if you now look at the oscillation probability, in this case, a nu mu to nu e appearance, this is given by the same type of two neutrino expression that I showed a few slides back. You have the sine squared 2 theta term, the sine squared of x, which is just this relation now of delta m squared L over 4e. And so you can look at it in the two cases. If you want to see what happens when you modify theta, this would be the expression that you get, or in the other case, when you are only modifying delta m squared. So you get a new term, a new expression for this oscillation probability. Now, you also need to consider the characteristics of the actual experiments that are happening in the relevant timescales. So of course you have the intrinsic timescale of the ultralight dark matter, but you have then also the timescale, the source to detector distance, the rest of the time resolution of the detector, and the running time of the detector. So for the analysis that we want to make, you want to consider only a case in which tau phi is within the upper bound of tau e and tau d. And you look at the different experiments, Diabe, Dune, Juno, Camlan, etc. You determine what are those timescales, and so what would be the number of events. And here also is a summary of the type of oscillation probability that these experiments are sensitive to. So reactor neutrino experiments are always sensitive to electron neutrinos, for example. And so you can look at the time average modulations in the case the tau phi is smaller than tau r, and you get the value of the mixing angles, and this is, you can solve this very easily, and you use the best experimental results on the mixing angle. And on the other case, you get the mass modulation, and you see then how, in this graph, you're seeing the change in the oscillation probability as a function of the energy when you have no modulation coming from the ultralight dark matter, which is the blue curve. And then as you turn on this eta delta related to the mass modulation for values of 0.1 and 0.2, you see a modification in the oscillation barriers. So barrier heights. So this could be detectable and measurable in, say, for example, the Dune experiment. Okay, I think I'm going to skip the Camlan. Another option is to look for CP violation, and in this case, I'm just illustrating this with a toy model in which you can actually consider this Y matrix now is complex and could be purely imaginary. And in this case, you can define this quantity epsilon, which is just a ratio of mu over the sum of M1 plus M2, and epsilon is going to be much smaller than 1, but then you can look at the modified PMNS matrix. It's going to get corrections that are proportional to epsilon and epsilon squared, and this is again going to modify your mixing angles, your mass squared differences, but very importantly, it's also going to modify the CP violation that you had in the PMNS is now going to be modified to be given by this new term here. And what is very interesting to note in this case is if you look at the probability of nu mu to nu e, it's going to be exactly the same as the probability of anti nu mu to anti nu e but it's a time average effect, and it's not because CP violation is equal to 0. So that's actually an interesting thing to see. And you can get a bound on the value of epsilon 0 and the modulation of eta delta using different experiments. I'm going to skip this part as we're running really short on time, and I wanted really to leave some time for questions. But you can see in this, you'll have the slides later on, the future sensitivities that you can have in different experiments to try to measure this. And just let me stop here in saying which are the summary of the current bounds and future sensitivities for these modulation parameters in this case, and which are the relevant experiments. You have all the summary here for current experiments and here for the future experiments. So this is an alternative way of trying to see the existence of ultralight dark matter, but looking at neutrino oscillation physics. And this is kind of the main message that I want to convey at this time. I also want to just finalize with one more thing. One of the projects that I was involved with was in this Latin American Strategy Forum for Research Infrastructure. And it was the first time that there was a strategic planning process done with input from the community in Latin America. And there was a really, first a physics briefing book, and then a strategy document that was developed as a result of that. But I want to flash here are all of the activities that are going on in the different countries, the participation of the different types of experiments that are either astroparticle or cosmology experiments, or neutrinos and dark matter experiments, or high energy nuclear experiments. And this is a nice summary of all of the activity. This was done several years ago, and we have now started a new process to update this information and to see for the next period, what should be the Latin American strategy for the activities in these fields. So to conclude, producing the observed matter-antimatter asymmetry also requires extensions of the standard model. Viable models can be explored with current and future experiments. Generating neutrino masses also requires physics beyond the standard model. And these right-handed neutrinos or heavy neutral leptons are a viable mechanism and can also produce the baryon asymmetry. Dark matter continues to be an intriguing puzzle in cosmology and particle physics. Experiments have significantly explored regions in parameter space of diverse models. And as you see throughout the talk, key concepts that I've been talking about have been annihilations, decays, freeze out, abundance, symmetries, and signatures. So thank you very much.